Go look at practice question set number 1 that we did over the weekend. Question number 1 says, a 47-gram golf ball is hit with an initial velocity of 70 meters per second at an angle of 30 degrees up from the horizontal. What's the vertical component of the ball's momentum? Firstly, I want to circle that grams. Why? Well, because that's something that will lead to a silly mistake. And in all likelihood, okay, out of 30 of you in this class, probably 10 of you end up making a mistake because of that grams to kilograms thing, unless you draw attention to it so that you don't forget to convert it later on. I'm going to circle this as well, or underline this vertical component. I know that I was chatting with a couple people on Friday, and I can't remember if it was this class or the other class, and we were talking about the components, and I missed that myself. I was looking for the horizontal component as I was trying to explain it to a couple people. It's not the horizontal component, it's the vertical component. The reason that I was going with horizontal component as I was explaining it is because I just wasn't paying close enough attention. Okay, I was making a silly mistake. Like you guys will make silly mistakes if we don't draw attention to things that will lead to silly mistakes. So we are looking for the vertical component of the momentum. Okay, we've got the mass in grams, although we have to convert that to kilograms. And then, of course, we've got a velocity at this angle of 30 degrees. Now, if you had me for physics 20, okay, if you didn't have me for physics 20, you're going to know what to do. It's not like, it's not like you guys didn't learn this stuff. You did just as much as my class learned this stuff. Except if you were in my class, you learned a little phrase, a 5-word phrase that should be starting to come to your mind right now. Anybody who was in my class last year, do you remember what that 5-word phrase is? This is your hint. I don't like funny angles. Good. I don't like funny angles. Every time we see an angle that's not like 0 or 90, we, in our minds, repeat that phrase. I don't like funny angles. It becomes automatic, and that's good, because when we see these angles that aren't 0 or 90 degrees, we know that we have to do something with it if we're automatically thinking, I don't like funny angles. Well, what do we got to do with it? Well, we got to break it into its x and y components. In this case, the vertical component, which is the y component. So let's do that now. To do that, we take it off to the side here. We draw it. Okay, there's my 70 meters per second. And there's my angle right here, 30.0 degrees. Now I'm going to complete that triangle. This is my x side. This is my y side. Now, usually at this point, I would resolve this and get the x component and the y component. But in this case, since I'm only looking for the vertical component of the momentum, I don't need to bother with x, right? I'm just going to deal with the y component. So the y component of this triangle is what? Which side of the triangle is it? Is it opposite, adjacent, or hypotenuse?
Opposite.
It's opposite. Hypotenuse is always the longest side. The hypotenuse is touching the angle. You can see that the hypotenuse, the longest side, is touching the angle. So is the adjacent side touching the angle. The other one, the one that's opposite the angle, not touching the angle, is called the opposite side. So if we're looking for the opposite side and we have the hypotenuse, let's use the sine function here. Say sine 30 degrees is equal to opposite over hypotenuse. We end up solving for the y component there, ends up being 35.0 meters per second. So once we've done that, okay, once we've said in our minds, I don't like funny angles, and then we've gotten rid of the funny angle and changed it into an x component if necessary and a y component, then we never use that 70 meters per second again. It's done. It's dead to us. We never use it again. Now, if we're looking for the vertical component or the y component of the momentum, all we're going to do is say P is equal to m times v, but the y component, vertical component, is m times the y component of the velocity, which we just found, right? 35 meters per second. By the way, why don't we have to worry about a y component of the mass? We had to worry about a y component of the velocity, but not the mass. How come? Good. Mass is a scalar. It doesn't have a y component. Just like last week we talked about kinetic energy. Speed, scalars, right? We don't worry about x or y components of that or positives and negatives of that. So we're just going to say for this one, the mass, which is 0.0470 kilograms. Or if you check your data sheet, you say grams to kilograms is 1,000 or 10 to the 3. We could have said 47 0.0 times 10 to the minus 3. Same thing, right? Saves me from moving the decimal place over. Times it by y velocity, 35.0 meters per second. And when we do that, we end up getting 1.65 kilograms meters per second. So the answer for that ends up being A, of course. Okay, number 2 says, which of the following units are correct units for momentum? I really shouldn't have assigned this question. This becomes easier after today. It's doable. It was doable over the weekend, but it was a lot more challenging over the weekend than it would be if you were doing it tonight. So I apologize for that, but because I did assign it, we're going to go over it here right now anyways, even though it would be easier to go over it tomorrow here. Which of the following sets of units are correct units for momentum? Well, we remember momentum as kilograms meters per second, which is absolutely correct. Right? That's the standard units for momentum, but there is another set of units you're going to see later today that we can use for momentum as well. Now, what I'm going to do here, because of what we've learned and what we haven't learned at this point, we pretty much have to, with this, take each option and just go kind of guess and check. Guess A, check it. Guess B, check it. Guess C, check it, until we get the right answer. Okay? So here's how we're going to do that. I'm going to guess A, and I'm going to check A. A joule per second, a joule not per second, but joule times second. That's the same thing as saying a kilogram times meter squared per second squared times second. Now, if you're having trouble figuring out where that came from, think about this. Joules comes from energy, right? Kinetic energy is 1/2 mv squared. Kilograms times meter squared per second squared. Or you could say it's mgh, which is kilograms times meters per second squared times meters, which is kilograms times meter squared per second squared. Does that make sense? So a joule is a kilogram meter squared per second squared. Now, if I simplify this, I got a seconds on the top and seconds squared on the bottom. It becomes kilograms times meter squared over seconds. Is that the same as a kilogram times meters per second? No, it's not. It's close. Okay, but that doesn't count. Close doesn't count. Okay, let's try the next one. Newtons times, so this one isn't the answer. Newtons times meters. Well, let's replace a Newton with a kilograms meters per second squared. Where does that come from? Mass times A, acceleration, right? Meters per second squared is acceleration. Mass times acceleration times meters. Okay, we simplify that, becomes kilograms times meters squared per second squared. Is that the same as a kilogram times meters per second? No. We can't cancel the squared, right? Because it's not the same term on the top as the bottom. It's meters on the top, seconds on the bottom. So that doesn't work for us. Let's try C, Newton seconds. Now, again, a Newton is equal to a kilograms times meters per second squared, which, right, that's m times A, mass times acceleration, meters per second squared, times a seconds. Well, we got a seconds on the top, a seconds on the bottom. That cancels. We're left with kilograms times meters per second. Is that momentum? That's it, right? So the answer is C. A Newton second is the same thing as a kilogram times meters per second. Okay? Do you see that analysis? That, like I say, this question becomes dramatically easier after today's lesson, after we do what we're going to do today, but it's still doable over the weekend. Hey, how many people ended up getting that right? Good. That's not bad at all, actually, given the difficulty of that over the weekend. Number 3. Some of you guys might kick yourself on number 3. It says a 2.00 kilogram cannonball is fired out of a cannon at an angle of 30 degrees to the horizontal. The cannonball reaches the top of its path. Its momentum has a magnitude of 800 kilograms meters per second. What was the horizontal component of the cannonball's momentum when it left the cannon? So the horizontal momentum at the top is 800. That's the magnitude of the momentum, the total momentum. So in other words, there is no vertical momentum at the top, right? Well, there shouldn't be. You know there shouldn't be, right? Because the velocity vertical at the top is what? 0. Horizontally, we don't know what it is, but it's something. So therefore, if it has a velocity, it has a momentum. No vertical momentum, but it does have horizontal momentum. What do we know about the vertical speed when it goes up and down? Does it stay the same or does it change? Changes, right? We accelerate at negative 9.81. So it slows down vertically as it goes up and speeds up vertically as it goes down. What do we know about the velocity horizontally as it goes from start to finish? What is it? Horizontally? It stays the same. Right? The horizontal velocity doesn't change. Remember projectile motion in physics 20? The horizontal velocity doesn't change. All right. If this is the horizontal momentum at the top, then what's the horizontal momentum right here? And here, and here, and here, and here. It's the same. The vertical momentum changes everywhere, but the horizontal momentum doesn't because the horizontal velocity doesn't change. So the answer for that one is B. And finally, number 4 says a 1,200 kilogram car traveling north at 20 collides with a 1,000 kilogram car traveling south at 24. What's the total kinetic energy and the total momentum? Big difference here is that kinetic energy is a scalar. Direction doesn't matter. Momentum is a vector. Direction does matter. So let's find the kinetic energy first. Let's say EK is equal to 1/2 m1 v1 1/2 m1 v1 squared plus 1/2 m2 v2 squared. So we got 1/2 of 1,200 times 20 squared plus 1/2 of 1,000 times 24 squared. And when we do the math there, it works out to be 5.28 times 10 to the 5 joules. So the answer is either going to be A or B as a result of that, 5.28 times 10 to the 5. I think if you made this one negative, I think you're going to get 4.8. Does that happen? If you make this one negative? But you shouldn't make it negative, right? Because it is kinetic energy is a scalar. So we don't pay any attention to direction for that. Now, for momentum, we do m1 v1 plus m2 v2. That's 1,200 times 20 plus 1,000 times negative 24. And when we do the math there, it works out to be what? 0. Yeah, 0 kilograms meters per second. Or, hey, now we could say 0 kilograms meters per second or 0 Newton seconds. You know now as well, right? They gave me the numbers in kilograms meters per second, though, so that's what we'll go with. My answer ends up being B, 5.28 times 10 to the 5 and 0. How many people got that one? Good.